Now we take up the last and the very important topic from atomic model, and it is nuclear motion. That is, the motion of nucleus will be taken into consideration. So let's remind ourselves that in Bohr's atomic model, one of the assumption was we assumed nucleus to be infinitely massive, and that is, nucleus was assumed to be at rest. Now there are situations where a nucleus cannot be taken at rest. We have to consider motion of nucleus. Now when such situation arises, it is dealt with the concept of reduced mass. So in nutshell I can say, in all the situation where we have to consider motion of nucleus, when the motion of nucleus is pronounced and it can no longer be neglected, the effect is accounted by using the concept of reduced mass. Let's try to learn this concept. Now this topic has been picked up by IIT JEE at various occasions. There have been problems from this topic, so we have to understand this topic in detail. Now let's first talk about a situation where nucleus is moving. Now in situation where nucleus and electrons both are moving, so instead of saying, earlier we said in Bohr's atomic model, it is electron that revolves around the nucleus. Now here we will modify our statement by saying that when motion of nucleus is taken into consideration, it is more appropriate to say that electron and nucleus both are revolving around common center of mass. Now let's try to understand how such systems are handled, where motion of nucleus is taken into consideration. So please have a look on the diagram shown on the screen. So we can say the motion of nucleus is taken into consideration when the physical properties of system, here in general atom, are affected significantly compared to the situation when nucleus is assumed to be stationary. When the motion of nucleus is accounted, so it is more appropriate to say that both electrons and nucleus revolve around their common center of mass. Let's say R is the separation between electron and nucleus, so we can write R is equal to Rn plus Re. Rn is the distance of center of mass from the nucleus, and Re is the distance of electron from center of mass. Now by the very property of center of mass, we can write M and Rn will be equal to Me/Re. Now we know one of the property of center of mass, and that property says center of mass of any system is the point about which mass moment is 0. That's why the relation Mn Rn is equal to Me/Re. Now when we solve these two equations, we get the value of Rn as Rn is equal to Me into R divided by Me plus Mn. Similarly, we get the value of Re, and it is equal to Mn into R divided by Me plus Mn. Now let's try to evaluate some of the properties of this system. Let's attempt to calculate moment of inertia of this system. Now by definition, moment of inertia of this system will be moment of inertia of electron plus moment of inertia of nucleus about center of mass. So we can write moment of inertia, if I denote it by I, is equal to Me/Re square plus Mn Rn square. Just now we have calculated the value of Re and Rn. When we make substitution for Re and Rn, we get the expression for moment of inertia of the system where nucleus is in motion. Now when we make calculation, so we get the final expression of moment of inertia as I is equal to mu/r square, where mu is called reduced mass of the system, and the expression for mu will be Mn divided by Me plus Mn. Now let's consider one more property of the system. Let's say we are interested in calculating the angular momentum of the system. Now angular momentum is a vector quantity. So here the angular momentum of the system will be angular momentum of electron plus angular momentum of nucleus. Now both the electron and nucleus are revolving in same sense. Now for the separation to remain same, the time period will be same for both. That is, angular speed will be same for the both. So here the angular momentum due to electron as well as nucleus will be in same direction. So angular momentum L for the system will be ME VE RE plus MN VN RN. In terms of omega we can write it will be ME omega RE square plus MN omega Rn square. Now when we make substitution for these values for Re and Rn, we get the angular momentum of the system. And the final expression for angular momentum of the system is L is equal to mu omega r square. Again, mu is the reduced mass of the system. The expression for reduced mass of the system is Me Mn divided by Me by Mn. Now let's understand first of all why it is called reduced mass. Now if we just leave the term of mass of electron in numerator, so we are left with the expression Mn over Me plus Mn. Definitely the value of this expression is less than 1. So that's why we call it reduced mass.